Welcome to the lecture on maximum likelihood. Maximum likelihood is a procedure, a statistical procedure for guessing. It's not, well, we talked about averaging, which is a procedure for guessing. It's quite universal, averaging. Maximum likelihood is a little more particular. It's used in very special circumstances. When it can be used, it does a decent job. Actually, all it has to do is do better than guessing. It has to give us a little edge on not doing anything, on not knowing what to do. So let's see what it is. It's a little tricky. It's not trivial. Once you get it, and we show an example, you'll understand it. But it is not a trivial procedure. The maximum likelihood procedure, well, here's the way I like to say it. Let's list all the possible estimates. Remember what an estimate was? We said that something causes the data. Some parameter causes the data. Something, some situation, some real. If the book were, let's do it this way. If the book were 9 inches wide, then the measurements would be around 9 inches. If the book were 10 inches wide, the measurements would be around 10 inches. So we go and we take measurements, and our measurements are around 9 inches, 9.1, 8.9, something like that. And we have to decide whether the book is 9 or 10 inches. Well, since the data is around 9 inches, we say the book is 9 inches. The true width of the book gave an influence to the data. And now we look at the data and we try and figure out what gave rise to it. That's the general problem in estimation. In maximum likelihood, we have a particular method of solving for that which we feel is the most likely of the situations, the parameters, the things we want to estimate. Okay? So what I say to do is list the possible estimates, those things which you could pick, like the 9-inch book, a 10-inch book, a 12-inch book. Then take your measurements. Now sometimes the measurements come first. That's okay. You may have a bunch of measurements and you want to do a maximum likelihood procedure, so you then list the possible estimates. So you have measurements and you have the possible estimates, those values of the parameter that you might want to pick. Now what you do is you calculate the probability of the measurements, of the observed, of the measurements, as if each of the estimates were correct. In other words, say if this were a 9-inch book, what would my measure? What's the probability that my measurements would be 9.1, 8.9, and so on? If my book were 10 inches, what's the probability that it would be 9.1, 8.9, and so on? So you assume the estimate is correct and calculate the probability that the measurements would occur. Now that can be done. That's a forward probability type of calculation. That's not too difficult. The maximum likelihood estimate is the estimate which shows the highest probability. That is, the maximum likelihood. Probability and likelihood are really the same thing. We use the words interchangeably. Excuse me. The probability and likelihood. So when we calculate these probabilities, we find out that if it's a 9-inch book, it's likely to have 9.1, 8.9 as the measurements. If it's a 10-inch book, it's not very likely to have 9.1 or 8.9 as the measurements, actually much less likely. And therefore, the 9-inch book is the maximum likelihood estimate because the likelihood of the data, assuming 9 inches is true, is higher than the likelihood of the data assuming 10 inches were true. That's how the maximum likelihood estimate procedure works. Well, let's do a better example. Let's do a situation which you can possibly relate to. Let's say I have some dice. Here are some special dice that I created. There's 4 different kinds of die. One of them has a 1 and goes up to a 6. That's the normal die. That's, okay, this pair here. Cool. Starts out at 1, has different sides, they go up to 6. Another pair of dice starts out at 2 and goes up to 7. All right? So there's 2, 3, 4, 5, 6, 7 on that pair of dice. This pair of dice starts out at 3 and goes up to 8. This pair of dice starts out at 4 and goes up to 9. There's no 1, 2, or 3 on this. There's no 2 or 1 on this. There's no 1 on that set of dice. Now, that's the dice situation. And someone's going to pick a pair of dice out of a bag of dice mixed up of this kind. And they're going to roll it. and they're going to tell me what they rolled, how many dots facing up on the pair of dice. And as a result of their data, I'm going to have to pick which pair of dice it was. That is it this, these two, or these two, or these two? Actually, I'm not going to go quite that far. We'll see exactly what I'm going to do in a moment. But I have to centrally pick which dice it was. Well, the possibilities are you can get a 1 and a 1. That is, I'm using the lowest number on the die so we can distinguish the die. I can get, my pair of dice can be a 1 and a 1, or a 1 and a 2, or a 2 and a 1. It can be a 1 and a 3 and a 1, or a 2 and a 2. It can be a 1 and a 4 and a 1, a 2 and a 3, and a 3 and a 2. It can be a 2 and a 4, 4 and a 2, a 3 and a 3, a 3 and a 4, a 4 and a 3, or a 4 and a 4. Those are the only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different combinations of pairs of dice. Some of them look alike, but this is the first die picked, this is the second die picked. So there are 16 possibilities, some of which look alike. I'm just going to distinguish between them by the sum of the lowest two numbers. So this is, I'll call this situation 2, this situation 3, this situation 4, this 5, this 6, this 7, this 8. So as far as I'm concerned, there's only 1, 2, 3, 4, 5, 6, 7 different kinds of things I have to guess at. So someone's going to pick a pair of dice, one of these 16 combinations, roll it, tell me what they got, and I'm going to have to pick which of these 7 groups they belong to. Chances of guessing correctly are small. Notice there are at least 7 different groups, so there's maybe a 15% chance that I'm going to guess right at best. Or if you want to say, well, the best really, one trick way to do it is to say pick 5 all the time, because there are 4 out of 16 possibilities. If these 16 possibilities are equally likely, and they would seem to be if the dice were just even numbers sitting in the pile, then I have 16 different situations I could have, 4 of which are this. At best, if I picked 5 all the time, the best I could do is 25%. I could guess right about 25%, because 25% of the time I would be in this situation. 4 out of 16. That's 4 16s. So if I guess without thinking about this, I would guess one of these numbers, and then I'd be right 1/7, which would be about 15% of the time. But if I was smart, I'd pick 5 all the time, and I'd be right 25% of the time. So, in general, our chances of guessing are pretty small, 25%. Well, statistics is not here to do things correctly all the time. It's not an absolute thing. What we do in statistics is try and guess a little bit better than we would have if we didn't use statistics. So we're going to try and come up with a procedure that'll do better than 25%. I can do 25% by using, well, common sense, by picking 5 all the time. The question is now, can maximum likelihood increase our chances of guessing correctly? All it's got to do is increase the chances, and it's a decent procedure. So what I do is an experiment. And since we don't have a class here, we can't really do the experiment. We'll just have to imagine it. Here's the experiment I do in the big class. Pass out these dice. Everyone picks a pair of dice. Just sticks their hand in, picks out a couple. And then they toss. Well, they know which dice they have, the lowest 2 numbers, so they know which category. When I guess a 5, they'll be able to tell me whether I'm right or wrong. So first thing they do is note the sum of the lowest 2 numbers. They know which category I'm in. Then they roll the dice 10 times and record each value and add up the 10 values. All I need is the sum of those 10 values. I'm going to take the sum of those 10 values. I'm going to calculate the probability of that sum if the dice were coming from the 2, 3, 4, 5, 6, 7, or 8 category. And I'm going to pick the category which gives me the highest likelihood of obtaining the number that they get. Let's say they got a 56. We'll take that as an example and carry it through. They rolled a 56 on 10 rolls of the dice. Okay, check the chart. See if the maximum likelihood procedure is correct, and estimate the probability of guessing correctly by finding the proportion of correct guesses out of how many I did. All right, so that's the procedure we do. Everybody picks a pair of dice, notes what category they belong to, rolls it 10 times, gets a sum, then checks the chart I'm going to show you to see if to see what my guess would be. For any number they come up with, I have a guess as to which die it comes from by calculating the probabilities. I'm not going to make you calculate the probabilities. I will have done it. And then we'll see if I guess right, and we'll keep a score. And here's the chart. Now, it doesn't mean a whole lot to people who don't do the experiment, but this is the chart that people who do the experiment get to see. If they roll 20 to 75, dice 2. So I guess on the one where 56 was rolled, I would pick normal pair of dice. Nothing wrong with those dice. If they rolled 97, for instance, I would say it's dice number 5. That is, 5 is the lowest, sum of the lowest two numbers. If they said they rolled 120, I would say the lowest number is the lowest pair of numbers, sum to 7. And now each person does that, checks to see what my guess would have been. I don't have to guess. They tell me. They can check and see what I would guess. I'm going to guess according to this chart. And then we keep a little score. What we do is we make a score, correct and wrong. And we keep a running tally. What I used to do in the class wasn't as big as it is now, is keep a running tally of what's going on here. And when we're all done, and what used to happen, very interesting, the corrects and the wrongs used to be very, very close. Sometimes it would be more correct, sometimes, each time there was a wrong which was more than the number of corrects, we used to count off 5, and you could easily tell what the score was. And every time the wrong was more than the correct, people would be, yay, yay, and it was all over. There might have been 1 or 2 more wrongs than corrects, and let's say correct was only 48% correct, and it was 52% wrong, and, 52% wrong, they would scream and holler and say, we won, we won, we won. And the answer is, did they win? Did they win? If they beat me, and I was wrong 52% of the time, and right 48% of the time, did I lose? The answer to that is no, no, no. I was not fighting against a 50%. I'm not fighting against the students. I am working against a 25% guess rate. If I knew nothing, if I didn't use maximum likelihood and I just guessed, the best I could do is somewhere between 15 and 25%. And using maximum likelihood, it went up to 48%. 48% is quite a significant improvement over the 25% that I could have gotten the other way. So no, I didn't lose. I really stomped on it. But I wasn't stomping on a game of penny tossing. I was stomping on a game where I could only win 25% if I played the game according to the usual rules. Okay, let's review. The maximum likelihood procedure. What you do is you list the possible estimates. In this case, list the possible lowest numbers, 2, 3, 4, 5, 6, 7, 8. Those were the lowest groups that we had. Those were the groups that we had, the lowest sum of the lowest two numbers. List them. Take the measurement, like we said 56. Take the measurement. Now, calculate the probability of the observed, that is the 56, is if each of the estimates were correct. So calculate how likely the probability of rolling a total of 56 with a fair pair of dice, with a dice that sums to 3, with a dice that sums to 4. So actually I grouped them together because it didn't, any one of the dice, for instance, when you talked about 5 dice, you could have gotten 2, 3, 3, 2, 4, 1, and 1, 4. You could have used any of those, and you would have had a pair of dice which added up to 5, which in group 5. Well, it turned out any one of these pair of dice had the same likelihood, the same probability of rolling a 56. And so I grouped them together because I really can't distinguish which of these pair of dice was used, only that it came from that group. And that's why I made the game the way it was. At any rate, I calculate the probability of the observed, 56 say, for each situation, group 5, group 4, group 3, group 2, group 7, group 8, and then I pick out the largest. The maximum likelihood estimate is the estimate which shows the highest probability. That is, the maximum likelihood of the observation. Simple? Well, it's simple when I say it. It's not that trivial when you're thinking about it. The problem is you have to sort of work a little probability a little backwards. Instead of just calculating a probability. You get the estimate first, and then you calculate the probability of that estimate. Rather than calculating probabilities of all possible estimates, you calculate the probability of only that estimate. And the thing that's changing is the possible estimates, the possible values, not the measurements. Okay. All I can do in summarizing is say a maximum likelihood estimate is an informed guess. Sometimes it's good informed guess, sometimes it's a bad informed guess. There's really no way that we can tell in advance how good it's going to be, except that it's better than guessing. It's an informed guess. That's what we're here to do in statistics, make informed guesses. Some experience tells us a maximum likelihood is the right way to go for this situation. Let's use it because it gives us a guess which is better than other procedures we might use. Okay? We're going to use maximum likelihood in the next lecture, so remember it.